Good morning. Today we are going to discuss how a Turing machine can be used for computing functions. For example, for addition is an operation, subtraction, two's complement is another operation. For all these operations, that means integer operations, we can use a Turing machine. So Turing machine as a transducer. Transducer means it's a computer of integer functions. Transducer means it's a computer of integer functions. For example, in Turing machine we use a unary number system. Unary number system means just only a single input symbol. For example, suppose that if you want to represent say 5, so that is represented as 5 ones. That means this is 5, or simply we call it as 1 raised to 5. That means in the Turing machine, suppose that this is the Turing machine, and in that tape 1 1 1 1 1, this one represents 5. That represents 5. So if you have, this is the unary representation. This is the unary representation of 5. If you want to represent say 6, you will have 4 5 6 number of ones, or you are going to have 1 raised to 6. That means in addition to this you are going to have one more ones. Okay, that is the unary number system. And all the inputs to the Turing machine, if it is an integer, then that is represented by the unary number system. In binary number system you have 0 and 1 as input symbols. 0 and 1 are symbols in the binary number system, whereas in unary number system we have only a single symbol, that means only 1. And if you want to represent say 100, then 100 ones you have to print on the tape. And suppose that you are going to have two numbers. For example, suppose that if you want to add two numbers A and B, suppose that you are going to, if you are adding say 10 and 12, then initially this is the input tape, and as you know, this is infinite to the left hand, and it is infinite to the right hand also. That means these are all blanks and these are all blanks, and in between you have say 10 here. That means 10 number of ones, 1 raised to 10 number of ones, followed by, here you can have any delimiter, whether it is blank or you can use it as 0. 0 is the delimiter. Then afterwards you have 1 raised to 11 means 11 number of ones. And if you are adding these two, after doing that operation you have 1 raised to, so see, this is 12 and this is 1 raised to 12, and after addition you have 1 raised to 22. That means 22 number of ones, and the last one that becomes blank, and this you have to make it as 1. And this is the way you are adding. Anyway, unary number system is having only a single symbol, and any integer is represented by that much number of ones. Okay, now we are going to discuss how this can be achieved. For example, now I am going to have addition of two numbers in Turing machine. Addition of two numbers. Initially that will be in state Q0, and here you have 1 1 1 etc. up to 1, followed by 0, and here you have a set of ones. Okay, these are all ones. what you're going to do is, initially that will be in state Q0, and you're going to skip all the ones. You're going to skip all the ones, and once you reach this 0, you have to make it 1. Again you are moving right, and when you see a blank, what will happen? That means here you have 10 number of ones. After that there is a 0, and here you have 12 number of ones after that. That means including this 0, 10 plus 12 plus 1 0, that means you have 23 locations in between this blank and this blank. Now you have to make this 1, and after that moving right, once you reach this B, you have to make the next symbol left to that a blank. Finished. That means after doing this, you have 22 number of ones there. So for that, what you are going to do is, initially that will be in state Q0, and in state Q0, if you are reading 1, suppose that the input symbol is 1, you are going to stay in the same state, and you have to replace that 1 with 1. That means you are keeping that 1 as such, and you are moving right. Okay, that means upon encountering all the ones, you are going to skip all the ones until that 0. That means 1 1 right means you are staying in the same state Q0, and you are moving right. Okay, so next one is, upon encountering 0, what will happen? So if the Turing machine or the finite control happens to see, or if it is reading a 0, what will happen? If it is reading a 0, you have to make that also a 1 and move right. That means stay in the same state. That means if you are reading a 1, what will happen? If you are reading a 1, then you are going to keep it as such. If you are reading a 0, you have to make it a 1 and again moving right. That means again moving right, and once you reach here, what will happen? If there is a blank symbol, if the finite control reads a blank symbol, what will happen? It is switching to a new state Q1. This is the new state Q1, and upon reading a blank symbol, you have to keep that blank symbol as such, and you have to move left, and you have to switch to Q1. In state Q1, if the first one you have to make it, that means upon encountering a 1, that means here after reaching here you have moved left, and here you have to make the first one. That means the first one immediately left to the blank symbol, you have to make it a blank. For that means you have reached Q1, means you have read that blank symbol, and afterwards you have moved 1 position to the left. Now if it is reading a 1, what will happen? You have to make it a blank and move right or left. That means this is the accepting state. Q2 is the accepting state. Once you have reached this Q2, that means you have completed this. That means this is the final state. Okay, that means this is the Turing machine. Starting from here, this Turing machine, what does it do? That means it is adding 2 numbers. That means in your input tape, 2 integers are written in unary representation, and once you do this, after doing all these operations, that means in Q2 if you are reading a blank, in Q2 if you are reading a blank, then this is accept. Okay, this is accept. Blank, blank and accept. This is here you have 10 and 12 in your tape, and that is separated by a zero, a single zero. And once you do this, that means starting from state Q0, if you are reading all this, and if you process it, so after doing all this, 22 ones will be there in this tape, and that is the representation of unary 22. That is why these two are added. Okay, subtraction you have to do yourself. Subtraction, do it as an exercise. And now I will show you how 2's complement is generated. 2's complement. Okay, how 2's complement is generated. Subtraction, you can do it as an exercise. See, what is 2's complement? So I am going to show you how 2's complement is generated. Say 1 0 1 0 1 1 1 0 0 1. Okay. Now when you are taking the complement of this is 0 1 0 1 0 0 0 1 1 0. And if you are adding 1, what will happen? This is 1 1 1 0 0 0 1 0 1 0. I'll show you another example. Then 1 0 1 1 0 0 1 0 0 0. Suppose that I'm going to find the 2's complement of this. First, initially you have to find the 1's complement. That means here 0 1 0 0 1 1 0 1 1 1. When you are adding 1 to this, what will happen? 1 plus 1 0, 1 plus 1 0, 1 plus 1 0, 1. Then 1 1 0 0 0. See, if you compare this is the original binary number, and this is the 2's complement of that. 2's complement of that. And here you can see that a property of this 2's complement compared to the original number. That means initially you have another example 1 0 0 0 0 0 1 1 0. Suppose that this is an example, and the 1's complement of this is 0 1 0 0 1 1 1 1 1. And when you are adding 1 to this, 1 plus 1 0 0 0 0 0 1. Okay. Then 0 1 0. So 3 examples I have shown you here. See, here from right to left, this is the first one. You are going to keep it as such. When you compare this number, the original number and its 2 complement, initially you have a 1, and you have copied that to here, and now all the numbers to the left of that first one you have to complement this. That means 0 becomes 1, 0 becomes 1, 1 to 0, 1 to 0, 1 to 0, 0 becomes 1, 1 to 0, 0 to 1, and 1 to 0. That means from right to left, you have to search for the first one. And you have to copy that one as such. And to the left of that, you have to complement all the numbers. See here you are moving from here to here. You are searching for the first one. Up to that, you have to copy all the zeros. That means you have copied the 0, copied the 0, copied the 0, and you have copied the first one. First one here. And to the left of that, all, that means here this much. Up to this point, all numbers have to be complemented. That means 0 to 1, 0 to 1, 1 to 0, 1 to 0, 0 to 1, 1 to 0. Okay. Here, see, listen here. Here from right, this is the first one. From right, this is the first one. And 0, 0, 0, 0, 0. As per our rule, you have to skip or you have to copy all the zeros from right until the first one. Until the first one. That means you have copied all the zeros here. First one also copied, and to the left of that. That means for these many numbers, what you are going to do is you have to complement. This is the way you can find the 2's complement of a number. So I am going to have a Turing machine for that. Going to have a Turing machine for that. See, the rule is from right to left. From right to left, search for the first 0. Not first 0, search for the first one. Search for the first one. Search for the first one. Until that first one. Until that first one, all the zeros have to be, all zeros including the first one has to be copied to the 2's complement number. That means search for the first one. Suppose that you have a number, say 1 0 1 1 0 0 1 0 0 0. Simply, if you want to write the 2's complement for this, what you are going to do is from right to left, search for the first one. Including that first one, you have to copy, and from here you have to complement 1 1 0 0 1. Okay. This is 1 and this is 0. So this is the 2's complement representation of this number. That means there is no need to complement it, then add 1 to it. What you can do is from the right, you have to copy all the zeros until the first one, and that first one also has to be copied to here. Then all the numbers, including, that means all the numbers, all the binary numbers to the left of this has to be complemented. Okay. So I am going to have, see, in state Q0, what you are going to do is you are scanning from left to right. That means your input is printed on this tape. Say 1 0 1 0 1 1 0 1 0 0 1 1. Suppose that this is the input. And now you are searching or you are scanning from left to right. And once you reach the last symbol, then only you can start the complementation. Now skip all the ones and zeros until the first blank. See, suppose that here you have the input tape. here you have the input tail, and this is 1 0 1 0 0 0, and to the right of that you have blank blank, and to the left of here also you have blank. That means in between you have, this is the number. We are going to find the 2's complement of this. For that, what you are going to do is, here initially that will be in state Q0, and initially that will be in state Q0, and Q0 on receiving 0, we are going to skip and move right. If 1, move right. For zeros and ones, you are moving right. This is the start state. And once you encounter the first blank, move left. That means that is a new state Q1. And in state Q1, that means here Q0, now you have, when Q0 is reading this blank, what will happen? It is moving left, and now you are in state Q1, and this is the input symbol you are going to read. And in state Q1, if there is a 0, what will happen? You have to copy that to, or you have to keep that 0 as such. That means the result also you are going to print it the same tape. Now you have to keep this 0 as such, move left. You have to keep this 0 as such, move left. Keep this 0 as such, move left. And when you are encountering, or when the finite control sees this 1, it is switching to a new state. That means if there is a 0, you have to keep that 0 as such, and you are moving left. And when you are moving left, what will happen? That means you are moving left, moving left, moving left. That means now it is in state Q1, and it is reading this 1. What will happen? It is switching to a new state Q2. And in state Q2, that means that one also has to be copied. 1, 1 left. That means it is keeping this 1 as such. That means the first one from the right has to be copied. That means that is there in the 2's complement. And now all the elements to the left of this has to be complemented. So 1, 1 left means if you are reading the first one from the right, that is copied to the output, and you are moving right. Now all the elements, if it is a 0, you have to make it 1, move left. If it is a 1, you have to complement it. That means if 1, you have to make it 0. If 0, you have to make it 1, and again moving left. Okay. And if there is a blank, that means moving left, 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 you have to keep this blank as such, and moving right. This is the accepting state Q3. This is accepting state. Okay. So this is that means here what you are going to do is you are going to complement 1 0 1 0 0 0. Okay. What is the 2's complement of this? When you are doing this, what will happen? This is 0 1. 1's complement is 0 1 0 1 1 1. When you are adding 1 to this, 0 0 0 1 1 0. When you are doing this, what will happen? Upon state Q0, you are going to skip all the zeros and ones. Once you reach here, you are moving left, and in state Q1, you are skipping all the zeros until this 1. That means you have copied. That means you are skipping all the zeros until the first one. That one also you are going to skip. Now, when reaching here, you are in state Q2. You are in state Q2. In state Q2, if you are reading 0, what will happen? You have to complement this. That means you have to make this 1. Again moving left, you have to make it 0. Okay, that is 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0. This is the way 2's complement is generated. Now I will show you how a unary number is converted to a binary number. For that, how a Turing machine can be used to convert a unary number to a binary number. For example, suppose that you have a unary number 10, 1, 1, 1, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, 10, 1. Okay. When you are converting this to its equivalent binary number, that number is 1, 0, 1, 0. This is the binary number. That means 8 plus 2 is equal to 10. This is having 10 number of ones. 10 number of ones. Okay. Now, how this is done? You are scanning from left to right. That means, suppose that this is the Turing machine and this is the Turing machine. And initially, you have these 10 ones in this, and initially you are in state Q0. And after reading the first one, after these are all blank, this is blank, this is blank, 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 blank. Okay, and to the right of this also blank. Okay, now first one. After reading the first one, you have to make it X. That means you have to make this X. Then going left. Now, once you are in state Q0, you are reading the first X and you are switching to a new state Q1, and now you are switching to a new state Q1. Once you have read this one, a single one, then you have to update this. That means after reading each one, you are going to increment the binary number. Increment the binary number. For incrementing that, we are going to use a technique. For example, initially you have all blanks. Suppose that initially all blank. Then from right to left, if you want to increment this, that means nothing is there. And from scanning from right to left, if you happen to see a single blank, you have to make that 1. That means after that, here you are having B, 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 B. That means 4 blanks afterwards there is a 1. Okay. Now after that again, if you want, that means here from here you are scanning for the either a blank 0 or 1. That means you are going to store your output here. This is the location for your output. And once you have read a single 1, that means now you have to increment your output by 1. You have to increment your output by 1. And when you are incrementing this output by 1, this is the location of the output. And here scanning from right to left, this is the location where you are starting your output representation. Now, as it is a blank, you have to convert this to a 1. You have converted this to a 1. Again, you are moving right. You are skipping all these X's, and now you have reached here, and now again you are making a 1 to X. Again moving left, and when you happen to see a 1 here after this X's, if you happen to see a 1, so for representation, for easier representation, I am going to use Z and Y. That means I am going to use 0 is represented as Z, that means 0, and 1 is represented as Y and Z. So initially, instead of this 1, I am going to use Y, and from right, after making this X1, you have to increase this by 1 or you have to increment this by 1, and from right to left, if you happen to see a 1, what will happen? You have to make it a 0. That means this y you have to make it a 0. That means you have to make this a 0. Okay, 0. Again move left. Until a 0 or blank is occurred. Until the occurrence of either 0 or blank. Either 0 or blank, you have to make it 1. That means again moving left, you have a blank, and that blank has to be replaced by a 1. That means the representation of 1 is y. That means you have yz here. That means yz means 1 0. This is y is 1 and z is 0. So this is 1 0. That means after reading 2 ones, now it is 1 0. 1 0 means it is a representation of 2. Again you are moving right. You have to replace this 1 by x, and now we are going to increment this. That means once you reach here, you happen to a 0. That means you are searching for either a 0 or a blank. You have to move until a 0 or blank is occurred. Here you have 0, so make it y, or that 0 has to be replaced by 1. Then there is no need to go further. This y by b, that is 1 1. That means here you have read 3 ones. That means the representation of 3 is 1 1. Representation of 3 is 1 1. Now again you are moving right. You are going to read the next x. Okay, you are going to move the next x. That means now it is 4 ones you have read, and now the representation here should be 4, and again you are moving left until you see an z or b. Why? You are searching for either 0 or blank. That means here searching for 0 or blank. Here you happen to see y. You have to make that y z. Move left. Again this y has to be replaced by z. Again moving left, you happen to see the b, and that blank has to be replaced by y. Actually, this is the representation 1 0 0. This is the way. Now again see, moving right, you are making this x. You have to increment this. You are searching for either 0 or blank, and here you happen to see the 0. Then you have to make this y. That means 1 0 1. And this is the way we are going to do these operations. So the Turing machine equivalent to this is Q0 in state Q0. Initially that will be in state Q0, and Q0 upon reading 1, what will happen? Q0 on reading 1, you are going to replace that with x, and you are moving right. Q0 on reading 1, that 1 is replaced by x and moving right. In state Q0, if you happen to see an x, you are going to state Q1. You are not moving right, actually you are moving left. This is not right. 1xl. For reading the first one, you have to make it an x, and you are moving left. In state Q1, you are searching for either in Q1, if you happen to see an x, nothing has to be done, again move left. If you happen to see while moving left, if there is a y, while moving left, if you happen to see a 1, you have to make it z. Okay, that means if you happen to see y, you have to make it z and move left. Okay, then in this case, if you happen to see a 0, what will happen? If you happen to see a 0, you have to make it y and move right. Sorry, here you have only 2 states. Again you have to skip to state Q0. Only 2 states are needed, and from this state you can switch to state Q0. In state Q1, if you happens to see in state Q1, if you happen to see X, then you have to keep, that means you are scanning. That means once you have read this one, make it X, and while you are moving left, you have to skip all the X's. That is X, XL. And once you reach Y, you have to convert that Y to Z. That is given here. Y has to be replaced by Z, and once there is an Z, that Z has to be replaced by Y. Z has to be replaced by Y and move to Q0. That means now you can move right. Okay. Now instead of Z, if there is a blank, that blank also has to be replaced by Y and you can move right. Okay. You can move right. Again, and in state Q0, that means here in state Q0, you can skip all the Y's. You can skip all the Y's. That means here, if you are in state Q0, Y right, Z right, and X right. Okay, all the X's you have to skip, all the Z's you have to skip. There is no possibility for Z, and you have to skip all the Y's. Okay, Y's also has to be skipped until there is a 1. You are going to make that 1 an X, and once you are in state Q1, again you are skipping all the X's. That is why XXL, moving left. Then if you happen to say Y, you have to replace that with the Z, and if you happen to say Z, you are going to switch to a new state, previous state Q0, replacing this Y, Z by Y. And if there is a blank, that also has to be replaced by Y. This is the Turing machine which is accepting or which is converting a unary number to its equivalent binary number. Thank you.